Okay, and we're back. So what we're going to do is give the common symbol used to represent the following types of radioactive decay. For A, we have alpha. Okay, and so on that one, we have two different answers we could write. First, we have our helium nucleus, beta symbol. Either one there. And for your test on this kind of portion, as long as you have one of those, that would be acceptable to me. Okay, for proton, we have two different ways of showing that one. A 1, a P, or a hydrogen nucleus. Okay, for neutron, we really only have one way to write that. And so we have a 1, a 0, and an N there. Any questions about number 1? Don't be shy. Okay. Go on to number 2. Okay, we're going to be labeling the following from either being most penetrating, we'll label that one with a 1, to least penetrating, labeling that with a 3. Okay, so which one do you think would be the most penetrating? Gamma, that's right, because it's not a particle at all. It can go through anything, right? Almost anything. What would be the least penetrating of those? Alpha. Very good. They're very large particles, so they tend to bounce off of things. Okay, and beta would be there in between. Good. All isotopes having an atomic number greater than that of the element blank are radioactive. Bismuth. Great. So you gotta just put your Bi there. The most stable isotopes have a blank number of protons and a blank number of neutrons. Even and even for that one. The most unstable isotopes, which combination do they have for number of protons and number of neutrons? Odd and odd. To me, that is very odd. That affects it, but it does. Number 5, which of the following elements undergoes nuclear fission reactions to provide the primary source of energy from the sun? It is hydrogen. Number 6, which of the following particles cause a nuclear fission reaction in a uranium nucleus? We have a neutron. Very good. We have that uranium bombarded by a neutron. Okay. On number 7, in the nuclear decay process called K capture, which change occurs to the atomic number of the capturing atom? Okay, so remember that a K capture process, if we drew what that looks like, right, it's an electron that's captured. And so think about what's going to happen to the bottom number of that isotope. What's going to happen? It's going to be decreased, by 1. Very good. Okay, when an atom undergoes radioactive decay by emitting an alpha particle, which change occurs to the atomic number of that atom? Decreases by 2. So, well, let's look at it. We have our alpha particle, right? And we know it's going to be, since it's emitted, it's going to be on the right side. And so, yes, it must be decreased by 2 there. Very good. Number 9, several units have been developed to quantify the effects of radiation. There's a whole list of them right in your notes. Which of the following is not such a unit? So which one of those did not show up on that list? Rutherford. Okay, on number 10, let me move this on up. A sample of radioactive material is allowed to remain undisturbed for a time equal to 4 half-life periods. What fraction of the original amount of material remains after that time? What'd you put on that? 1/16. And so if we look at that, if we have our T sub 0, and let's say we have 1, for my first half-life, I would have how much of that? 1/2. Okay, for my second half-life, I would be at what? 1/4. Third half-life, I would be at 1/8. my fourth half-life, which is the one they're asking about, would be that 116. Good. Number 11, what type of decay would you expect an isotope of plutonium-244 to undergo? Flip to my other page there. We know plutonium, yes, alpha. It's greater than bismuth. And so if something is greater than bismuth, it's going to usually undergo alpha decay to quickly become stable. Okay, so let's write an equation for this reaction. We're starting with our plutonium-244. My atomic number is 94 here. Okay, so let's decay. We're decaying. And we are expecting it to undergo alpha. So we have our helium nucleus over here for our alpha particle. And so what does that mean for my mass number for our daughter nuclide? What must it be? 240. And its atomic number must be 92. And so what element does that correspond with? Uranium. Very good. So that's my balanced reaction for that. Right here? You could flip those if you'd like to. You could totally flip those if you'd like to. As long as they're on the right side of your arrow, then that's great. Okay, for number 12, for each of the following reactions, give the symbol and the name of the species indicated by X. Okay, so to balance this, let's see what we need our X to be. We would need a mass number of 4, and we would need an atomic number of 2 there. And so what kind of particle would that be? That's an alpha particle. It would have to be a helium, right? A helium nucleus. So that's our symbol. And we call it alpha. For part B, okay, we're on the left side of our equation now, but we see a 55 and a 55. So we know our top number must be 0. What must our bottom number be? A -1. And so what kind of decay is this? Yeah, this is K capture, okay, because we have our electron being captured, right, since it's on the left side of our equation. So our symbol, we write that again, that's fine. And this is K capture. Okay, for part C, we have our X on the right side of our equation. We have a 12 and a 12 over here for these carbons, which I like putting my totals there. So I have a 24 for the top. I have a 12 for this bottom. And so what must be the top number for X over here? I need it to equal 24, and I'm already at 23. That's right, I need a 1. And then for 12 and 11, I need something there. What do I need? A 1. And so what kind of particle is this? Proton? Or we could have called it a hydrogen nucleus, either one there. And so let's call it proton. Very good. Okay, on this next one, we have 96 and 2. I'm going to put my totals here. 98, we have 42 and 1, so 43. My bottom number, I have 43 and 43, so we know it must be a 0 over here for our X. And then we have a 98 and a 97. So we must have a 1 up top. And so what kind of particle is this? It's a neutron. Yeah. And our last one here for this section, we have a 40 and a 40. So we know our X must have a top number of 0. And a 19 and an 18. So our bottom number must be a, what do we have there? A +1. And so what kind of particle is this? Positron emission. The type of our decay. Positron emission. Good. If we saw this particle, but it was on the left side, what would we have called it? A capture. Good. Okay. Let me erase that though. All right, number 13. What isotope results if an atom of uranium-234 decays by emitting 3 alpha particles in succession? Okay, so we're going to start with our uranium. My atomic number is 92 there. We're going to emit 3 alpha particles. We have 3, a 4, and a 2. You're welcome. And so let's decide what our daughter nuclide must be. Okay, so we have a 3 times a 4 here for that alpha particle, which is 12. So what must be my top number for my daughter nuclide? 222. Okay, and then for the right side here, looking at that alpha particle, we have 3 times 2 for our atomic number, and we have a 92 over here. And so what must be my atomic number of my daughter nuclide? 86. And so what kind of element is that? That's a radium. We can go ahead and write that on the line, because I believe that's what they wanted us to do, is write the daughter nuclide. That results. Okay, on number 14, what isotope results if an atom of thorium-232 decays by emitting 1 alpha particle and 2 beta particles? Okay, so we have our 232 thorium, atomic number 90. And we're going to decay. We're going to emit 1 alpha and 2 beta. Okay, so remember that 2 out in front of your beta, you'll have a 2 times a 0 for the top number, 2 times negative 1 for your electron, or for your bottom number there. That's how that'll work. Okay, and so what must be the top number for this daughter nuclide? I have 228 also. Okay, what must be my bottom number? 90. Okay, and so that would be what element? Still thorium. I guess we can rewrite it over here if we want to. Okay. Good. Questions so far? Questions so far? Okay, let's look at 15. 15. It says the actual mass of carbon-14, an isotope of carbon, is 13.9676 grams per mole. Calculate the binding energy of this isotope in joules per mole if the mass of a proton is, they give you the mass of a proton, and then they give you the mass of a neutron. What kind of problem is this? What are we going to have to do first? To calculate binding energy, I can't just jump in and do that. I'm going to have to determine something first. I'm going to have to determine that mass defect first, yes. And so we know that our mass defect, or mass deficiency, right? It's going to be negative, we know that. It's going to be equal to our mass of our nuclide minus the mass of our protons and neutrons. Okay, so let's decide, figure out real quick how many protons and neutrons we have that we're working with. Okay, so how many protons do we have for carbon-14? 6. Okay, so we'll have 6 protons. How many neutrons then do we have in carbon-14? 8. Okay, so we're going to have our mass defect equals, what's our mass of our nuclide? Yeah, it's given to us. Very good. 13.9676 We have grams per mole minus, I didn't give myself much room there. We have our mass of our protons. Okay, so we'll have 6 times 1.00783 grams per mole plus our number of neutrons times mass. I'm going to put it down here. So we have how many neutrons? We said 8. So we'll have plus 8 times our mass of our neutron. That is also grams per mole. Sorry to bring that down here. That is ugly. Okay, so when I do this math, okay, I'm going to go ahead and write this again. Okay, for this last part, I have minus 14.11634. Okay, and so then I get an overall defect of negative 0.14874. Okay, and then my unit there should be grams per mole. Is it okay to leave it like that? No, change it to kilograms. I need it to be kilograms per mole so that when I enter it into E equals mc squared to calculate binding energy, that I get the correct units there. And it must be a kilogram per mole to do that. So we're just going to make our number smaller by 3 places. So we'll have negative 0.000144874. Now our unit is kilograms per mole, and that's what we need for the next part, which is calculating the binding energy. Okay, so to calculate binding energy, we know our E binding energy is equal to mass times the speed of light squared. We're substituting that mass defect in for m to calculate binding energy. So our E is equal to mass in kilograms per mole times our speed of light, and then we must square that. So our speed of light is 3.00 times 10 to the 8 meters per second. And we're squaring that. And so I get an overall energy equal to negative 1.3386 times 10 to the 13th joules per mole. And so that's why we needed our mass defect to have kilogram per mole as a unit, because we end up with this kilogram times meter squared over second squared, which we know equals a joule, and then we still have our mole on the bottom. And that's our unit for our energy there. Okay. We need to probably round that to 3 sig figs because of our speed of light. So let's round that to 1.34 times 10 to the 13th as our final. Any questions on number 15? Oh, thank you so much. That is a negative. Yes. Thank you so much for that. Okay, let's look at 16. 16. If 0.32 inverse years is the value of the radioactive decay constant for a certain isotope, what is the half-life of the isotope? Okay, so what they're giving us here is K. Okay, so our K, our decay constant, right, which is unique to every isotope, is equal to 0.32 years to the minus 1. And we want to know what is our half-life. And so our relationship there is our half-life is equal to 0.693 divided by our K, which is 0.320 to the negative 1. And so when I enter that in my calculator, I get a half-life equal to 2.2 years. That's all we had to do on that one. Okay, on number 17, the decay constant is 0.0862 days to the negative 1 for the spontaneous decay of iodine 131. If 10 grams of this isotope are allowed to stand for 16.1 days, how much iodine 131 still remains? So on this one, okay, they give us a K constant. I'll go ahead and write that down. Okay, and we're also given some information about how much of this isotope we're starting with. Okay, so that is an N sub 0. So that would be our 10.0 grams of the isotope, 131 iodine. We're solving for our N. We want to know how much is left after our T equal to 16.1 days. And so that's our T equal to 16.1 days. Okay, so my formula, since we're dealing with grams, we want to use the form that has natural log equal to N over N sub 0 equals negative K times T. And so we'll have our natural log. We're solving for N, so we're just going to leave it as that. N sub 0 is 10.0 grams. Equals our negative K, 0.0862 days to the minus 1, times our time elapsed, which they want 16.1 days. And we need to make sure our units here match, and they do. So we are okay to go on with our math there, solving for N. Now to get rid of this natural log, we need to multiply it by the inverse natural log. It'll make it go away over here, but then I'll need to bring in inverse natural log on this side, which I will enter in my calculator. Okay, so I'll hit the second function, natural log, and I'll enter 0.0862 times 16.1 and get a number for that. And so I get my N over 10.0 grams equal to, and the number I got for the right side is 0.249619. So then to get N, we just multiply that by our 10, and we get 2.50 grams. Any questions on that one? Okay, on 18, the decay constant, I'm going to write that down, is 0.131 year to the minus 1 for the spontaneous decay of cobalt-60. How long, okay, so I know I'm solving for an elapsed time this time on this problem, must a sample of this isotope stand in order that only 35% of it will remain? Okay, so now on this, what I'm going to do is I'm going to say that my starting amount is 100. And if I only have 35.0% of it remaining, what must my N equal? It must equal 35. 35 would be 35% of 100. And so now we're going to plug this into our equation. Okay, same equation as before. So my N is 35. N sub 0 is 100. Remember, we always want to make sure the N sub 0 is larger. It's another thing we can look for when we're working these to make sure we have that part set up correctly. Solving for time this time. So now what I'm going to do with that natural log is I'm just going to enter that in my calculator, just the way I see it here. I'm going to hit natural log, parentheses, 35 divided by 100, close parentheses, and I get negative 1.05 when I do that, equal to the negative 0.131 years times, to the negative 1 times t. So now I just need to divide my negative 1.05 by my negative 0.131 to get time. And so I get time equal to 8.01. And then my unit, because of my K constant, should end up being years. Questions on that one? Okay, number 19. The half-life of sodium-24 is 15 hours. So my T sub 1/2, 15 hours. What is the value of the constant for sodium-24? So they want to know K. Okay, so what is our relationship there? We know K is equal to 0.693 divided by our half-life, which is 15.0 hours. And we get a K equal to 0.0462 hours to the minus 1. Okay, on 20, it says initially it is observed that a certain radioactive sample causes a Geiger counter to click 230 times per minute. That's an activity. Okay. After 30 minutes, the number of clicks per minute on the Geiger counter is only 125. What is the half-life of this sample? So on this one, we're given an initial activity of 230. Let's include our decimal there. Disintegrations per minute. Okay, we get a later activity after time has elapsed of 125 disintegrations per minute. We know our time is 30 minutes. And what they want to know is half-life. So what I'm going to have to do on that first is get K and then solve for my half-life after I've gotten K. So since they give me activities, I'm going to use this form of the equation. Let's plug in what we know. We have an A of 125, A sub 0 of 230 equals negative. We're going to solve for K times 30 minutes. On the left side of my equation, I'm going to enter natural log, just like I see it, 125 divided by 230. I get negative 0.60977 equal to negative K times 30. So I'm going to divide now by that 30 minutes. And I get K equal to 0.02033 inverse minutes. Okay, and so now that we know K, we know, I'm going to erase this here. Now that we know K, we can solve for our half-life. Okay, and we have half-life equal to 0.693 divided by our K constant. And so I get a half-life equal to 34.1 minutes. That's my final answer for that one. Okay. And I believe that's time for today, since it's Highlander time. So we're going to stop there. We will continue there tomorrow. Okay? Don't forget to like, comment, and subscribe.